Hey everyone, today we're diving into a Leetcode problem called Count of Interesting Subarrays. It sounds, well, interesting. Don't worry if it seems tricky at first glance. We'll break it down step by step and find an efficient way to solve it. Ready? Let's go. Alright, so what's the goal here? We're given a list of numbers called nums, and two extra numbers, modulo and k. Our job is to count how many subarrays are A. Subarray is just a continuous part of the original list, like maybe the second through fifth elements. Now what makes a subarray? We need to look inside the subarray, from its start index L to its end index R, and count how many numbers satisfy a condition, nums percent modulo equals k. If this CNT itself, when we take it modulo equals k, then the subarray is interesting. Phew, that's a bit of a mouthful, but basically, count the special numbers in the subarray and check if that count, modulo equals k. We need to find the total number of subarrays that pass this test. Let's walk through the first example. We have nums equals 3, 2, 4, modulo is 2, and k is 1. We need to find numbers where num percent 2 equals 1. First, the subarray just containing 3 modulo 2 is 1, which equals k, so the count CNT is 1. Does CNT percent modulo equals k? Is 1 modulo 2 equal to 1? Yes, so this one counts. Next, the subarray, 3, 2. 3 modulo 2 is 1, counts. 2 modulo 2 is 0, doesn't count. So CNT is still 1. 1 modulo 2 equals 1, yes again. This one also counts. How about 2, 4? 2 modulo 2 is 0. 4 modulo 2 is 0. Neither satisfies the condition. CNT is 0. Is 0 modulo 2 equal to 1? Nope, not interesting. Finally, the whole array, 3, 2, 4. 3 modulo 2 is 1. Counts. 2 and 4 don't. CNT is 1. 1 modulo 2 equals 1? Yes, it counts. So we found 3 interesting subarrays, 3, 3, 2, and 3, 2, 4. The answer is 3. Makes sense? Okay, the first idea that usually pops up is brute force. We could just try every single possible start L and end R for a subarray. For each subarray we define, we'd loop through its elements, count the ones that satisfy our num percent modulo equals k condition, get the count CNT, and then check if CNT percent modulo equals k. If it is, we increment our total answer. But how many subarrays are there? If the list has n items, there are about n squared divided by 2 subarrays. And checking each one might take up to n steps to count the special elements. That sounds like it could get really slow, maybe order n cubed, or if we optimize the counting a bit, order n squared. For large inputs, this probably won't be fast enough. We likely need a more clever approach. So how can we speed this up? Let's look at the core condition again. The count of special elements in a subarray, let's call it count, LR, needs to satisfy count, LR percent modulo, equals k. Whenever we need to calculate something about a range or subarray quickly, prefix sums often come to mind. Here, we're not summing the numbers themselves, but rather counting how many special numbers we've seen. Let's define a prefix underscore count array. Prefix underscore count will store the total number of special elements, where num percent modulo equals k, found in the original nums array from the very beginning, up to, but not including, index I. Now if we have these prefix counts, how can we find the count for a specific subarray nums? It's simply the total count up to index R, which is prefix underscore count, plus 1, minus the total count up to before index L, which is prefix underscore count. So count R is just prefix underscore count, plus 1, minus prefix underscore count. Substituting this back into our condition, we want to find pairs, minus prefix underscore count, plus 1, minus prefix underscore count, percent modulo, equals k. We can rearrange this using modulo arithmetic. Remember that AB percent m is the same as A percent m B percent m plus M percent m. Applying this, we're looking for pairs, p-takbikate, fichokwas, timings lagon jarbars where prefix underscore count, pichokwas, picharbars where bars way takbikate, timings lagon jarbars, kera prefix underscore count, plus 1% modulo, k percent modulo plus modulo, pichokwate. Since k is given, k modulo is just k. So we need prefix underscore count, percent modulo equals, prefix underscore count, plus 1, minus k plus modulo, percent modulo. This rearranged formula gives us a great idea. Let's process the array from left to right, keeping track of the current index r. As we go, we'll calculate the prefix underscore count up to this point r. Let's find its value modulo, call it current underscore mod. Now for this specific r and its current underscore mod, we need to know how many starting points L before or at r satisfy our condition. The condition tells us we're looking for previous prefix counts, prefix underscore count, whose value modulo equals a specific target value. Target underscore mod equals current underscore mod, k plus modulo, percent modulo. How can we quickly find out how many times we've seen this target underscore mod in our prefix counts so far? A hash map, or a dictionary in Python, is perfect for this. We can store the frequencies of each prefix underscore count percent modulo value and count it as we iterate through the array. Okay, let's outline the algorithm. First, we initialize our total count of interesting subarrays, result, to 0. We also need a variable to keep track of the running prefix count of special numbers. Let's call it current underscore prefix underscore count, starting at 0. Crucially, we initialize our hash map. Let's call it counts. We start it with one entry, the key is 0, and the value is 1. This represents the prefix count before the array starts, which is 0, and it's essential for correctly counting subarrays that begin at the very first element. Now we loop through the input array nums, using an index r from 0 up to the end. Inside the loop, first, check if the current number nums is special, nums percent modulo equals k. If it is, we increment our current underscore prefix underscore count. Next, calculate current underscore mod, which is current underscore prefix underscore count percent modulo. Then calculate the target underscore mod we're looking for, current underscore mod, k plus modulo, percent modulo. Now, the magic step, look up target underscore mod in our counts map. How many times have we seen this target underscore mod before? Add that frequency to our result. If target underscore mod isn't in the map, we add 0. Finally, we update the map. We increment the frequency count for the current underscore mod we just calculated. If current underscore mod wasn't in the map before, we add it with a count of 1. After the loop finishes, result holds the total count of interesting subarrays. We just return it. Alright, here's the Python code implementing that hash map approach. You can see the default dict, which is handy for frequency counting. We initialize it with counts, 0 equals 1. Then we loop through the numbers. Inside the loop, we update the current underscore prefix underscore count, calculate current underscore mod and target underscore mod, add the count of target underscore mod to our result, and finally increment the count for current underscore mod. Pretty neat, huh? So first up, we set up our tools. We create a default dict, int. This is like a regular dictionary, but if we try to access a key that isn't there, it automatically creates it with a default value of 0. Super useful for counting. We then immediately set counts, 0 to 1. This is super important. It represents the state before we've processed any elements, where the prefix count is 0. This allows us to correctly count subarrays that start right at the beginning of the nums list. We also initialize our running current underscore prefix underscore count, and the final result to 0. Now, the main part, the loop. For each number nums in our input list, we first check if it's does nums percent modulo equals k. We store 1 if it is, 0 if it's not. We add this 1 or 0 to our current underscore prefix underscore count. Then we calculate the two important modulo values, current underscore mod, based on the current underscore prefix underscore count, and target underscore mod, based on current underscore mod and k. Remember, target underscore mod is the value we wish a previous prefix count modulo had, so that the difference matches k. The crucial step, we look up target underscore mod in our counts map. Counts target underscore mod tells us exactly how many previous points L had the right prefix count modulo value, to form an interesting subarray ending at the current I. We add this number to our result. Finally, we update the map for the current state. We increment the frequency count for current underscore mod, because we've just encountered one more prefix count that results in this modulo value. So how efficient is this approach? We iterate through the input list nums exactly once. Inside the loop, all operations, arithmetic, hash map lookups and updates, take roughly constant time on average. So the total time complexity is directly proportional to the number of elements in the list, which we call big O of n, or order n time. That's excellent. What about memory? We're using a hash map to store the frequencies of the prefix count modulo values. In the worst case, the prefix count could keep increasing, but the modulo value can only be between 0 and modulo 1. So the number of distinct keys in our hash map is limited by modulo. It's also limited by n, the number of prefix counts we calculate. Therefore, the space complexity is order of minimum of n and modulo. This is also very efficient, especially if modulo is small compared to n. Alright, let's quickly recap. The problem involved counting subarrays based on a condition involving the count of special elements modulo. The brute force approach of checking every subarray was too slow. The key insight was to use prefix counts, counting the special elements up to each point. By applying modulo arithmetic, we found a relationship. We needed to find previous prefix counts, modulo m, that matched a specific target value, derived from the current prefix count modulo m and k. A hash map proved to be the perfect tool to efficiently track the frequencies of these prefix count modulo values, allowing us to find the number of valid starting points L for each ending point R in constant average time. This whole strategy resulted in a fast order n time solution with reasonable order minimum n modulo space usage. Hope that breakdown made sense and helped you understand the prefix sum and hash map trick. If it was useful, please hit that like button, maybe subscribe for more Leetcode explanations, or feel free to drop a comment if you have any questions or alternative ideas. And hey, if you're feeling extra supportive, the Boba Fund is always appreciated. Keep practicing, keep coding, and I'll see you in the next video.